Okay, in this video we're going to look at the idea of constructive and destructive interference. This is just a continuation of the idea of the superposition of two waves, but it's going to distinguish between situations which cause an increase in the amplitude by adding the sum of the two waves' amplitudes compared to a lower or a decreased amplitude because the waves don't match each other. Now, the easiest way probably to think about constructive and destructive interference is if we draw a couple of simple diagrams. So I'm going to draw two identical waves. These are going to be periodic waves though. So in the previous video we were essentially looking only at pulses, but now we want to be able to look at periodic waves. Okay, so here are two nearly identical waves. And what I'm going to do is I'm going to add those two waves together to give me a new result. And if you look at what's going to happen, you'll notice that this crest, which has a value of A, and this crest also has a value of A, that when I add those two together, I'm going to get something that is going to be equal to 2A. So the new wave is going to look something like this. And you'll notice that we have a much larger amplitude because the two waves are matching with each other perfectly so that their two amplitudes combine together to produce a very large amplitude. If we were thinking about the two main kind of waves that we're going to talk about, sound and light, what this would mean for sound is that we would have a louder sound. The two waves would combine in such a way that the combination was twice as loud, or much louder I should say, than the individual waves. And if we were talking about light, what this means to have constructive interference is it would mean brighter. So when two light waves interfere constructively with each other, they end up producing a brighter light. The light appears brighter because the amplitude is much larger. Now, how does it work when you have destructive interference? The similar idea that we're going to add the two waves together. So I'm going to add a wave that has an amplitude of A. But this time I am going to add it to a wave which is reversed, or that is to say out of phase with this first wave. So instead of going up, what I'm instead going to do is go down. So now I have a wave of amplitude A, and I have a wave down here of negative A. Oh, I wrote that like that. And of course, when I add positive A to negative A, the result is going to be complete cancellation. So instead of getting a much larger wave, what I end up with is a much smaller wave. And in effect, if this was sound, you wouldn't hear anything. There would be no noise at all. But when you have destructive interference, which you're definitely going to expect to hear, is the sound is going to be much quieter than it should be. The sound should be louder, but because the two waves are interfering with each other in a way that causes either complete or entire cancellation, as a result, we end up with a wave that is either much lower or doesn't exist at all. So for sound, that would be a much quieter sound, and for light, that would be a much dimmer sound. So constructive interference produces loud sounds and very bright lights, and destructive interference produces very quiet sounds and very dim lights. Now, there is a condition for periodic waves as to when will you see the periodic waves constructively interfere and when will you see them destructively interfere. So let's take a look at what is that condition, and this can be quite a tricky thing to really think about. Before I put anything down on the paper, what I would first like to do is to just use these simple paper clips as a way of demonstrating what do I need to do in order to produce constructive and destructive interference. So let's assume that the source of these two waves is over here to the left and it's coming from my finger. Okay, so my finger is producing this pink wave that's traveling off to the right in this direction, and also down here is a separate speaker, and that is producing the blue wave, and the blue wave is traveling like that to the right also. Now we're going to leave the blue speaker where it is, but I'm going to move the pink speaker, the one that's producing the pink wave, so that we can see under what conditions will I get things to line up. So right now, if the two speakers are right next to each other, I can see that, of course, they are producing identical waves. They have the same amplitude, same wavelength, same frequency, traveling at the same speed. Then the waves are going to match up, and I'm going to see constructive interference because I have crest matching with crest, and I have trough matching with the trough. Okay, now the question is, how far would I need to move it before I would see that situation come back into alignment again? So I'm going to take the speaker, which is here at my finger, and I'm going to start pulling it to the left, and you'll see that as I pull it to the left, the alignment doesn't look as good anymore. Now the waves are not lining up with each other, but if I continue moving them and keep pulling them further and further and further, you'll see that they will eventually come back into alignment. So now I have crest lines up with crest again, I have trough lines up with trough again, crest rest matches up with crest again, and I'm going to get constructive interference. And I can continue moving. Now if I start moving again, I'll lose my constructive interference. Now the waves don't match up with each other anymore. I'm going to continue moving them, keep moving them until eventually that crest will match up again with the next crest, and I will see constructive interference occurring again. So it turns out that how far away the detector is, so let's say I have a detector right here, well, that detector is going to hear a really loud sound because these two waves are constructively interfering with each other. They're going to produce a very large amplitude way up here, and as a result, the sound is going to be very loud. Okay, and as I continue to move that speaker back, I'll see that the constructive interference goes away, the sound gets a little quieter. Now as it starts to line up again, the sound gets louder. It's very loud right now when the waves match up with each other. I continue pushing that speaker forward, and I'll see that the waves will again eventually match up with each other. So what turns out to be important is how far is the detector or the sensor away from the two sources. Remember, we have to have two sources. We can't have constructive interference with just one wave by itself. Under normal circumstances. So let's take a look at what the math looks like behind this, and we'll see if we can't develop rules that tell us when do we get constructive interference, when do we get destructive interference. Let's assume for the purposes of this example that we are dealing with waves which have a wavelength of exactly 2 meters. Okay? That's going to be really important because it turns out that where the speakers have to be placed or where the source of the waves has to be placed depends a lot on the wavelength. It's extremely dependent on the wavelength. So let me draw a speaker over here on the left. Okay, and this speaker, we're going to leave it alone. We're not going to move it. This is going to be our D1, and we're going to put it at some distance away from your ear. Again, we're going to place the second speaker right next to it, and that is also going to be 20 meters apart from each other. Okay, in this situation, the two distances, D1 minus D2, and just for the record, we don't care whether it's a positive or negative number. It doesn't really make a difference. So let's just say the absolute value. So D1 is 20 meters between the sensor and the speaker, and D2 is also the same. So in that situation, what would end up happening is I would have 20 minus 20. That gives me 0. Okay, and in that situation, I will get constructive interference. And what essentially, realize what I need to do in order to produce the constructive interference is I need to, any movement that I make of one of the waves or the distances, I need to make sure that when I move it a full wavelength. So when the two waves match up at the initial position where they're both at the same distance, of course everybody matches up. But they will still match up as long as I move that second source so that it is exactly a multiple of the wavelength. As long as I move it so that the crests still match up, and that will always happen every time I move over one full wavelength. So what I'm looking for is to see a multiple of the wavelength, and in that circumstance, I'm going to produce constructive interference. So it turns out there's lots of points. It's not just one point of constructive interference. There's lots of points of constructive interference. So this leads to a value for, I'm going to call this property n. So n is equal to 0 divided by the wavelength, which is 2. That gives me the n equals 0 situation. Now let's imagine that I move the speaker a little bit. So let's try this situation. Let's say that in the second situation, D1 has remained the same. But I moved the second speaker back a little bit. And now it is at 22 meters away from the person's ear, away from the sensor. So now when I make this calculation, it's going to be 20 minus 22, which gives me a distance of 2. So when I calculate this property n, it's going to be 2 divided by 2, which is 1. Okay, and you can imagine other examples. So let's say, for example, 20 minus 24. That would be 4. That would lead to n equals 4 divided by 2. I'm always taking the difference between the two distances, and then I'm dividing by the wavelength. And if I divide that difference between the two sources' distances by the wavelength, if it comes out to be a whole multiple of the wavelength, then that is going to cause the crest to match up with crest, troughs will match up with troughs, and I will end up with constructive interference. Okay, so the question then is, what do you have to do in order to get destructive interference? Under what circumstances could you get these two waves to cancel out? It turns out that there's lots of circumstances where you can make that happen. So all of this is on the constructive side. So let's take a look at what happens with the destructive side. So let's say that we take that same speaker. These are all constructive, constructive, and constructive. So we have our speaker at 20 meters away from the person's ear. And now I'm going to move this guy just a little teeny bit. I'm only going to move him to 21 meters. Okay, so let's take a look at what happens when I move the speaker half a wavelength further away. So now I'm doing my D1 minus D2. And I'm going to end up with 1. When I go ahead and make this calculation for n is going to be equal to 1 divided by 2. That equals 1/2. Okay, that is going to produce destructive interference. And let's go back to the paper clips real quick so you can just visualize what's happening. So remember, if I move the source of the blue waves 1 full wavelength, then I get constructive interference still. Okay, but how do I get the destructive interference? Well, if instead of pulling, look at this crest. If instead of pulling this crest all the way over to the next crest, let me pull it only halfway. Let me pull it half of the wavelength so that this crest now matches up with this trough. Okay, this guy's going to cancel this guy. This guy's going to cancel him. He'll be canceled by this. This one will be canceled by here. All the waves are going to cancel out. So what I'm going to end up with, if I produce this circumstance where the waves are mismatched by each other by at least a half a wavelength, then I will get destructive interference. Now I can continue to move it. If I move it again to this position, I will again get destructive interference. So as long as I move the second source by a distance that's equal to half a wavelength, or any multiple of half a wavelength, then I will end up with destructive interference. So let's just take a look at a couple of examples of those. This is for the n equals 0 situation. I end up with n equals 1/2. Now let's say that I moved it, where would be the next position where I would expect to see destructive interference? Well, I would need to move it 1.5 times the wavelength away. And 1.5 times the wavelength would be 3 meters. So I need to move 3 meters further to the left. And if I do that, I'll end up with 20 minus 23. Sorry, absolute value. That's equal to 3. So now I'm going to calculate what value of n did I get. So that is n is equal to 3 divided by 2, or 1.5. That will also be a destructive interference. Where will the next position come? It'll come at 25. So if I do 20 minus 25, that gives me 5. That leads to an n of 5/2, or 2.5 wavelengths. Okay, essentially what I'm doing by subtracting the two distances from each other and then dividing by the wavelength is I'm trying to figure out, is it a multiple of the wavelength or is it a half multiple of the wavelength? If it's a full multiple of the wavelength, I get constructive interference. If it's a half multiple, then I get destructive interference. So let's set some rules that's going to allow you to actually calculate and know for sure and not have to guess whether you're getting constructive or destructive interference. So for constructive, the condition is that when we subtract the distances, what we should end up with is some number times the wavelength, a multiple of the wavelength, where n is equal to 0, 1, 2, 3, and so on. It goes on forever. Okay, there's any number of ways that I can produce constructive interference as long as the distance between the two sources is some multiple of the wavelength, then I will still end up with constructive interference. In order to get destructive, we have a similar condition, and that is that we need a half multiple. Okay, so 1/2 n times lambda, where n is equal to 0, 1, 2, 3, and so on. So the condition that you need to think about is whether the difference in distance between the two sources is a whole multiple of the wavelength or is a half multiple of the wavelength, and that's going to determine whether you get constructive or destructive interference in any kind of wave that you're that you're talking about.